Good afternoon, everyone. That's a great introduction, and thank you, Ross, for setting the scene. Thankfully, there's not too much duplication in what I'm going to cover. I'm an acoustician as well. I work for AECOM. We've got 100 people located around the world, and this is based on our experience and some case studies to do with tall and green buildings. I'd also like to thank my co-author, Dr. Peter Swift. He's a wealth of experience, and I thank him for his input. First of all, I'm going to start off in two parts for this paper. Just talk about some of the issues that we do come across with tall green buildings related to noise and vibration. And then, through a number of case studies, we'll talk about how we can address these and hopefully give you some practical advice to deal with these things, and also to look at what to deal with when you have similar projects. First of all, with natural ventilation, obviously very green, there's a weakness in the facade. There's an opening. Sound travels through air. I think everyone realises that. Air travels through windows, through open windows, so therefore noise travels through. With increased urbanisation, we're living closer to each other. There's more noise sources, and our old little friend there, Mr. Noisy down the bottom, is creating more of an issue. Trucks, transportation, aircraft, they're all to be considered with our green buildings with natural ventilation. And another issue that we've seen a few examples of recently with increased sun shading, and also perhaps more detailed small elements on balconies and the like. We're seeing a few more instances of aerodynamically generated noise. So I've got a few case studies and a few examples of that. And those examples are where the noise is generated on the sunshades or similar, and then transmitted through the air into the building, or generated by the sunshade and then travelling through the structure into the building. So thanks, Ross, for his introduction on the airborne and structure-borne noise. We've all seen the Vortex Shedding diagram from the Birch Dubai down the bottom. I'm talking about this on a smaller scale. You can get the same sort of thing with wind flow past smaller things like sunshades. Fairly impressive looking building. We're looking at wind turbines. Once again, fairly popular. I think there's been some good discussions as to their viability and whether they're a good idea or a bad idea. When there were some discussions on wind turbines the other day, I didn't actually hear anyone ever mention the word noise or vibration. So these things are noisy, and they do, or they can generate vibration. Once again, the noise they generate is related to the wind speed. Faster turbines means more noise, so you can get an airborne component. And also, if they're located and fixed to the building, you can get a structure-borne component. So I've got a bit more discussion later on this. When we were putting this paper together, we sort of thought about how we're going to frame this. Acoustics is a science, but there's an element of art. So trying to be truthful with you. There's things that are quite predictable, definite, probable and possible, and then there's our friend down the bottom, where it's pretty hard to predict, although it's possible that may occur. So I'm going to use this theme as I go through to do a few case studies. I think this is the easy end of the scale. Predictable and definite. Mechanical plant does make noise. We know that. It's generally mass-produced, generally well-tested, generally comes with noise data, generally well known. Cooling towers, chillers, pretty well known. Air handling plant. Chilled beams, perhaps a new innovation for green buildings. Fluid flow. And these can generally be controlled through fairly traditional means. attenuators, vibration isolation, although as Ross pointed out, those things are not always done. Important point to note is where you do have green buildings, generally there's perhaps less mechanical plant, which is a good thing, but a little bit of noise is actually a good thing. So in office buildings and so forth, a little bit of background noise gives you privacy and helps give you privacy and perhaps a little bit better amenity. So just be aware that you can actually get caught out by having a building that's too quiet. Our friend the truck there on the left, that's our noise source, and as we talked about before, open windows, noise path leads to a truck. Now, just bear with me here. That truck's a little bit bigger than the other truck, indicating it's a little bit quieter, but not a whole lot quieter. So operable windows don't really do much for noise attenuation. Okay, now I wouldn't like to hear a truck in my dwelling or my high-rise office building, but sometimes there's birds and there's wind in the trees, which are nice, so noise is not necessarily a bad thing all the time. Then with double skins, if they're openable likewise, perhaps they're for other purposes, for ventilation or for thermal as part of the green building. You see our truck reduces a little bit in size, but basically there's still a couple of openings there, so the noise is still getting in. If the outer skin was sealed, that would certainly improve the situation, although you've got to be careful about noise transmission between floors and between spaces, then through that void for privacy and other reasons. Our truck's getting smaller. This is another neat way of dealing with the issue, having fixed glazing and then subfloor or ceiling void ventilation. You can incorporate a little bit more noise attenuation, and it's a good way of dealing with the issue. And you could do that with or without the second skin. And we're getting a little bit better again. There are a couple of products on the market, a passive ventilator or a forced ventilator. So the one in the top right hand corner has got a little fan in it. So there's ways of getting air into the buildings while attenuating and hopefully having a green and acoustic benefit. Obviously this needs to be taken into account with the whole pressure loss and operation of the ventilation systems. Can you see the truck now? It's getting small. So with pretty much with fixed or double glazing, we can pretty much solve most problems, apart from right near aircraft runways and so forth. So yeah, we're generally pretty comfortable if we've got fixed glazing, double or single, depending on what the needs are. So that's a range of things. It really depends on your site and what sort of amenity you're looking for. Sometimes it's desirable to have noise intrusion, and you've got to find that right balance as part of the overall amenity of the building. There are many green rating tools which actually incorporate an acoustic component in their brief. While we're talking about glazing, I thought we'd just touch on so the different types, or the common minimum types of glazing that we might see, and using our analogy of the truck size again. What we're doing is we're comparing three glazing systems: 6mm glass, fixed 10mm glass, and then what I'd call a thermal double glazing. I wouldn't call it double glazing from an acoustic point of view. 6mm glass, 12, and then 6. And I'm not quite sure whether you can see it, but there's an RW rating, a weighted sound reduction index, which is an overall nice number, easy to use, good for people to understand. These systems are all about the same. The only problem is that the little purple line, which relates to the 6-12-6, has a nice dip. It's probably around the 200 hertz or so. Unfortunately, that quite often coincides with traffic noise, so the frequency of traffic noise. So that's why, even though it's a double glazed system, it doesn't necessarily provide you with much benefit over a single 6mm glass. So if you tell your client that they're spending twice the money on a thermal glazing and they're getting no benefit, sometimes they're a bit disappointed. whereby the 10mm glass is performing much better at the low frequency range where the trucks or traffic may well be dominating. So just be aware of that. You can get caught out on that quite frequently. Although, you know, on the converse, the double glazing or double thermal glazing is performing much better than some of the other systems at higher frequencies. I perhaps didn't explain the graph very well, but along the bottom is frequency, the sound frequency, like the bass is low and then, you know, treble is high. And then on the left-hand side is the sound reduction. Wind turbines. Once again, this is a current project. This is a, you know, fairly sexy green building. Wind turbines, very prominent. Once again, I guess there's a question as to how effective they are from a green point of view. But they do make noise. This is a graph showing typical noise levels for this is a fairly sophisticated wind turbine at some distance, but they're not quiet. And noise levels do increase with wind speed, so you'd need to consider, you know, what's the rate of wind speed, you know, and what noise you're going to expect. So how do we deal with these things? Selection, you know, where you can select a quieter one, go for it. Although based on projects we've seen so far, there's a real scarcity of information. A lot of the manufacturers are still fairly young in terms of what they're doing. As in they haven't been around for very long, maybe not the owners are young, but hence we don't have a lot of data on the emission levels, and also as the prototypes are changing, the noise emission data is pretty tough to get. But say you get that, and then you can look at location where you're going to put them. If you're fixed in where you can put them, then upgrading the facade, as we talked about before, is a good way of going. But please don't forget the potential for noise to pass back through the mounts as a structure-borne noise. So just be aware that you might need to mount it on an isolated mount. So we're moving on to the slightly more obscure. So I'm going to talk a little bit more about aeroacoustics. So we've got a few more pretty pictures of vortex shedding. So basically we're talking about sound generated by airflow, which is as a result of fluctuations in the pressure through interaction with structures and other elements. And once again, for the wind people out there, we're talking about fairly small scale elements, so we're talking about smaller vortex shedding, but at a much higher frequency. So in the range at which we can hear. Another variation to the theme is where we've got airflow interacting with a cavity, such as a flute or a void. And in these cases, all of these cases, the sound that we hear would be related to the frequency of the vortex shedding. I'm not sure if this is going to work, but is there a mouse? Aha. I just couldn't resist showing this, but this is a nice interaction between wind and structure, and what can go wrong when you get your structure tying in with the shedding frequency. So examples of that can happen. Probably in the work that we're doing, we're not dealing with that sort of scale of project. Hopefully no more bridges have fallen down since that one. But the same sort of thing can occur with smaller structural elements on buildings as they're becoming more articulated. And those resonances can, you know, translate into felt vibration or audible structure-borne noise. One project that I've got a bit of a case study on is Riparian Plaza. It was the tallest building in Queensland for a short time. It's a commercial office building at a lower level, and you can see some very nice penthouses at the top. We were engaged to look at the communications mast. Our client was concerned about the potential for noise and vibration to be generated at the mast and then transmitted into these expensive penthouses where these clients were demanding high amenity. So as another example of that Tacoma Narrows Bridge, whereby wind can interact with small structures, we felt there was a sufficient risk to the potential for that to occur with some of the smaller elements, like some of the meshes. You can see on the communications tower there's some small meshes there and small handrails and small ladders. We felt there was a need to mount the whole mast on rubber isolators to prevent any transmission of noise back into the structure, and bearing in mind that this mast was actually right out front of some people's balconies. So the detail there, hopefully you can see it somewhat clearly, is the mast is supported on a rubber pad, and there's a rubber pad above that, such that there's no steel-to-steel connection of the mast back into the building. So anything that's generated in that mast would be attenuated or mitigated by the rubber pads. It was quite a complex detailing exercise, as there were a number of mounting points. So that's been successful. We haven't heard of any complaints. So we're moving on to the predictable but possible. And we'll bring our lady back with the flute. So we're talking about potential for cavity interaction. So wind blowing past cavities can form a bit of a flute type mechanism. Helmholtz resonator, quarter wave resonator, there's a number of names for it. And we're going to go back to the Riparian Plaza. We're not using this example for the whole presentation, so don't get worried. But down the bottom, there's a little access door. So we're concerned about creating the world's biggest flute, a couple of 100 metres, well, 100 metres tall. So we took fairly careful attention to the opening down the bottom and minimised the openings in the door, rearranged the orientation where the door was located, and just double check the amount of likely wind flow past the door to make sure we didn't get our world's biggest flute. In terms of the actual flute itself, it would have been inaudible. It would have been in the what we call the infrasound range, below what we could hear, but people can still find that quite discomforting. And once again, this is quite near to where one of the penthouses were, so just be aware of these cavities. This is quite a large scale one, but you can get the same sort of thing in curtain wall detailing. Any gaps or holes you need to be aware of as a potential issue. So these are, now we're moving on to the tricky ones. And generally, these examples I've got here are about small repeating elements. So the first example is a sunshade for an office building. Wind tunnel testing of the sunshade showed that there was some fairly annoying whistling being generated, and we were called in to investigate and work out a solution. So what was going on? Essentially, in terms of the construction, it was a rectangular blade or series of blades, and that's probably where the part of the problem starts, is once you've got a lot of these things, if they're all making noise, it all adds up. The two lines are the measured noise level versus spectrum, and then the noise level on the left-hand side. And we were able to quite easily show that the whistling sound, 2,500 hertz, quite annoying, was shifting with wind speed, and hence is related to vortex shedding. So what do? It's actually quite easy. It was at prototype stage, so we just rounded off the edges. We didn't get a vortex shedding, and away we went. Another case study is a balustrade. This one's been installed. There's 12,000 fins, so this one's a bit of a problem. And you can see from the measurements it was quite tonal. When we say tonal, is the spike is quite obvious in the background, and I'm going to attempt to whistle. It probably sounds like... So if you hear that for hours on end nearby your residence, it's quite annoying. Now, okay, it was Possible that we could hear it in the field on relatively low wind occasions, a nice gentle wind. So we thought we'd put it in a wind tunnel. It couldn't be recreated in this wind tunnel. I'm not going to say who it was because there's another part of the story. So then we went to another wind tunnel. This is a special anechoic wind tunnel with a low noise airflow. Anechoic, you can see all the little wedges there, they're sound absorbing wedges, so it's quite nice and quiet. And with this arrangement we were able to recreate the noise from the whistling. It was actually a completely different mechanism from the sunshade, and it was the swirling of air around the cavity, wind flow in the cavity. It was being disturbance on the front edge was tying in with the cavity, and we're getting this quite nasty sound. So to be honest, thankfully no one actually asked us whether this was going to be okay or not, because I would have thought if we were asked whether this is going to be okay, we would have probably said, yeah, that'll be fine. We've done some calculations and said should be right, and we would have had trouble with our PI. But thankfully no one asked us that question. So what do we do about it? As we said, 12,000 of these things were installed. So there was a couple of options. One, put mesh on it, and that was shown in the wind tunnel to be quite effective. The second option was rounded edges, and we had a few access problems given it was at height. We've had trouble rounding them off and repainting them. So the final solution was an extruded rounded cap, which modified the disturbance to the void and helped solve our problem. So thankfully I'm on time, I think. This is my final slide. So I've tried to show you through some varying risk or varying likelihood noise and vibration issues for tall green buildings that generally, with a bit of forethought and a bit of thinking and a bit of testing, you can solve them. Some of them aren't always obvious, but we love the challenge. So thank you.